Welcome to the electrifying world of oxidation reduction reactions. Redox reactions are fundamentally about electrons changing hands. I like to remember it this way. Oil rake. Oxidation is loss. Reduction is gain. But here is the key insight. These always happen together. You can't have oxidation without reduction, just like you can't have a buyer without a seller. When zinc gives up electrons to copper ions, zinc gets oxidized while copper gets reduced. It's a perfectly balanced electron economy. Oxidation states are like molecular accounting. They help us track electrons. Think of them as the electron credit score for each atom. The rules are straightforward. Free elements are zero. Ions equal their charge. Oxygen is usually -2. Hydrogen is usually +1, and everything must add up to the total charge. It's bookkeeping that reveals the hidden electron transfers in chemical reactions. Spotting redox reaction becomes easy once you know the sign. Look for changes in oxidation states. That's your smoking gun. Common patterns include metals reacting with acids to produce hydrogen gas, combustion reactions where substances react with oxygen, and any reaction involving elemental forms of substance. When magnesium burns in oxygen, magnesium goes from 0 to +2, while oxygen goes from 0 to -2. Classic electron transfer. Here is where chemistry gets philosophical about cause and effect. The oxidizing agent causes oxidation but gets reduced itself. It's like a teacher who helps students learn while learning something new in return. Strong oxidizers like oxygen and fluorine are electron-hungry bullies, while strong reducers like lithium and sodium are electron philanthropists, giving electrons away readily. Balancing redox equations can seem daunting, but the half-reaction method breaks it into manageable steps. We separate the oxidation and reduction processes, balance each half-reaction completely, atoms and charge, then combine them so electrons cancel out. It's like solving two smaller puzzles independently, then fitting them together perfectly. Let's walk through a classic example. Permanganate oxidizing iron in acidic solution. Permanganate half reaction needs 8 protons and 5 electrons to balance, while iron simply loses 1 electron. To make electrons cancel, we need 5 iron atoms for every permanganate. The final equation shows the beautiful stoichiometry that emerges from electron balance requirements. Basic solutions add an extra twist to our balancing act. We start by balancing as if in acidic solution, then neutralize every proton by adding equal hydroxide to both sides. So hydrogen ion plus hydroxide ion makes water, and we cancel excess water molecules. It's like translating the equation from acidic to basic. Same fundamental chemistry, different chemical language. Standard reduction potentials are like the credit rating for electron acceptance. We measure everything relative to hydrogen, which gets a score of exactly 0 volts. More positive values indicate stronger oxidizing agents. They really want electrons. More negative values indicate stronger reducing agents. They readily give up electrons. It's a universal scale for electron affinity. Cell potential calculations follow a simple but powerful rule. E naught cell equals the reduction potential of the cathode minus the reduction potential of the anode. Alternatively, it's the reduction potential minus the oxidation potential. A positive cell potential means the reaction is spontaneous. It wants to happen naturally. Negative means you need to force it with external energy. Here is where thermodynamics and electrochemistry shake hands. The relationship delta G naught equal negative NFE connects cell potential directly to free energy change. A positive cell potential means negative free energy change, which means spontaneous reaction. The larger the cell potential, the more energy the reaction can provide. Please note that this expression, the delta G naught equal negative NFE, it's also called, the G here stands for Gibbs free energy. And note that the degree sign indicates standard conditions, 25 degrees Celsius, 1 mole concentration, and 1 atmospheric pressure. Redox reactions are everywhere in our daily lives. Combustion reactions power our cars and heat our homes. Hydrocarbons get oxidized while oxygen gets reduced, as metals give up electrons to oxygen and water. Even photosynthesis is a redox process, where carbon dioxide gets reduced to glucose while water gets oxidized to oxygen. Life itself depends on electron transfer. Industry harness redox chemistry on a massive scale. Metallurgy extracts pure metals from ores using reduction reactions. We literally steal electrons from metal oxides. The chloralkali process uses electrolysis to produce chlorine gas, hydrogen gas, and sodium hydroxide from salt water. Its chemistry as manufacturing, electron transfer processes creating the materials our society depends on. Your cells are powered by sophisticated redox machinery. Cellular respiration is essentially controlled combustion. Glucose gets oxidized step by step, with the released electrons captured and used to make ATP. Antioxidants like vitamins C and E protect your cells by sacrificing themselves to reduce harmful free radicals. Your body is a complex network of electron transfer process. So this is all for this lecture. Thank you and see you in the next one.